Good morning. Am I audible?
Yes, sir.
Okay, let's start. Is the presentation visible?
Yes, sir.
Okay. So we have been discussing about Lambda syntax. Let's do a quick recap. We did a very important Lambda expression of self-application in a bid to try to model recursion through Lambda expressions, which will be very, very required if we have to use functions as the first class objects. And we saw that direct self-application leads of infinite loop in Lambda calculus. So we formulated a Y combinator where we introduced a function parameter and then applied to a is the then we introduced the notion of fixed point. Fixed point is a value in the domain of a function, domain A of a function which maps from A to A, such that the value of the function at that point is same as the value of the parameter itself. So with that, we note that the Y combinator is basically Y combinator applied to a function f is basically the fixed point of the function. Y combinator applied to f is the fixed point for the function f. So it is called the fixed point combinator. And now we use this to model the recursive function, and we took the most common recursive function, that is factorial. And we saw that if we write the recursive definition of the factorial using a function parameter f in place of the factorial here, and then we can see that the Y combinator basically gives us the factorial function. And we evaluated this for few initial values of the factorial. Indeed is the factorial function. So now with this, we have a way to define factorial functions as lambda. Whether this is limited to tail recursion, because factorial recursion. A next example will say that that is not so. There is no such limitation. So we take Fibonacci recursion, Fibo, and this is a well-known recursion of Fibonacci. So what we do, we write this recursive definition in the form of the Y combinator. Say that lambda n, if you initially have f as a... Yes, please.
Your voice is breaking between.
Is breaking?
Yes, sir.
Is it clear now? Is it
Yes,
clear
sir.
now?
Yes, sir.
Okay. It's always some problem. So in the Fibonacci function, if we, in place of Fibo, if we use a function parameter f, we are on slide 66, and the Fibonacci parameter n, then you can write this in terms of a lambda expression. So first we have the first exit condition, if is equal to 0 n. If n is equal to 0, then it is 0. Else, if n is equal to 1, then it is 1. Otherwise, it is the addition of f applied onto n minus 1 and f applied onto n minus 2, addition of these two. And you would recall that we had mentioned that we are using if for a kind of a shortcut definition for the Boolean expression if that we generated from the lambda calculus, to just keep it handy. And we assume that testing for equality in natural numbers and subtraction of natural numbers and addition of natural numbers are taken to be predefined functions. So if we have this Y Combinator, then Fibonacci necessarily is Y Combinator applied to this functional, which is f underscore. So I will leave it as an exercise to you to show in complete steps that if you apply this onto 5, then you will get really get the value 5, which you should get. And also I leave a longer exercise for you to show that this actually is a correct Fibonacci function. So to do that, you have to use induction to prove that YF applied onto n is same as the recursive definition of the Fibonacci function. So what you do is you first prove it for 0 and 1. You evaluate this for 0 and 1. Then assuming that it holds for n, you have to show that it holds for n plus 1 and n plus 2, which will prove that inductively that this indeed is a Fibonacci function. So we then also see that is it only for, say, the linear recursion, because both your Fibonacci, though it is not a tail recursion, it is a linear recursion. So we apply, we check the Ackermann's function. I'm not sure if you are familiar with Ackermann function, but Ackermann function is defined in this way. So the first function has two parameters. That's the first complication. And if x is equal to 0, it is y plus 1. If y is equal to 0, then it is a simple recursion to Ackermann with x minus 1 and 1. But otherwise, it is a recursive call where the second parameter itself is a call to the recursive function, right? So it's multiply recursive. So if we evaluate this Ackermann function for few initial values of x, you can see that it initially was looking y plus 1, y plus 2, 2y plus 3, and so on. But very soon, it becomes heavily, very fast growing. So just for a specific value of y, I have shown the growth. Even from x going from 0 to 4, this has Ackermann 2 is 2 to the power 2 to the power 2 to the power 2 to the power 2. So it's 2 to the power of 2 to the power 4. So this becomes a 19,000 decimal digit number, right? So it goes very, very fast. It goes faster than any primitive recursive function. I'm not sure whether you know what are primitive recursive function. It's not very important in this context. If you have done theory of computation, you will know how primitive recursive functions are defined. But Ackermann function grows faster than any primitive recursive function. Now, interestingly, if you take this recursive definition of the Ackermann function, you can again write it in the form of a Y Combinator. Right? It's all that you need to do is to encode this in the form of a lambda expression. So if x is equal to 0, you have successor of y. Otherwise, if y is equal to 0, then you take predecessor of x and 1 and apply f onto it. And otherwise, you take predecessor of x and apply, and the second parameter is f applied onto x and predecessor of y. You will remember that we have defined the predecessor lambda expression also earlier. These are, I don't really expect you to take specific values and try to prove them or try to prove them by induction. This will be very, very long. But this gives us the idea that any recursive function can be actually written in terms of lambda calculus expression as well. Right? So that gives us a complete power of the fact that we can compute Ackermann function. That basically tells us that we can do anything that Turing machine can do. So lambda calculus becomes as powerful as the Turing machine. Some of the other aspects to consider, for example, in lambda calculus, we will always try to deal with a function abstraction which allows only one parameter at a time. But several functions will have multiple parameters, like sum as a and b. So sum is a function which has a domain of n cross n and maps to n. Now, how do I put this in the form of lambda calculus? Actually, one solution we have already seen, because we introduced the notion of currying because for this. But another that is frequently used, particularly is that we can, if there are say two parameters, then we can define the two parameters in the form of a pair. We can make a doublet out of that. How do we make a doublet? We can use the const operation in Lisp. Right? We have seen that, how to make a list of more than one element. And once we do that, then that becomes a single parameter. So typically we show ordered pairs in terms of corner brackets. So sum is applied onto the single parameter now, because it has been coupled together, and you have the value a and b. Now, how do we to get the specific values a and b for evaluation? How do you get them? Obviously, if this pair has been constructed by cons in Lisp, then a is head of that list, and b is the head of the tail of that list, right? Because head of this pair will give you a, tail of this list will give you a single element list containing b, and head of that list will give you the value b. So you can basically unpair using that. And the other approach of using multivariable functions that we will use is to use the idea of currying, that we will use, say, if we have add of a and b defined as a plus b, then we can define a new function, add a, the curried version, which is from n to n, which we have already seen, and then add a b, which takes two parameters, single parameter, and gives me a plus b. So accordingly, we can define the currying and uncurrying operation also. If you curry, then you will put that as a pair, and you can uncurry that by doing the head and tail out from the list construction. So overall, currying permits the partial application of a function. And what we are actually focusing on in lambda calculus is we can have higher order functions. And we have seen examples of that. Higher order functions basically are functions which which may take a function as a parameter, as well as it can return a function as a var. Right? So these are the examples of twice that we have already seen. So this is what is known as parametric polymorphism. Now, I'm going a little fast on this because these we have seen, the examples we have seen. I'm just pointing out that these are examples of different aspects of programming language concept that are being modeled by lambda expression. So twice is basically twice applies on a function, which is say from D to D, and it gives us a function from D to D again. So if we apply twice on square, which is from n to n, twice square is a function from n to n, which is the fourth power. So that this basically, so twice square with this cutting of with square, actually we get a new function. Right? So the function comes here as an output of this twice operation. So that is why we call all of these as higher order functions. Right? So defining a new function in this way is embodies the basic spirit of functional programming, which is where functions are mechanisms to take parameters as values and compute a value, but it can treat functions as first order objects, so that functions can be copied, functions can be passed as parameters to other function, and functions can be returned as a value from a function. Right? Let me briefly stop here to see if there are questions. Then I'll again continue. Any questions, friends? Significant addition of concepts here. It is just that we are, introducing some terms in terms of programming language concepts. Okay, there's no question, so let us move on. On to slide 77. Now, just talking about the very popular C++ language, we have, in terms of introducing lambda expressions and functional programming in C++, a concept of a functor. We will discuss about this in depth in module 6 when we talk about lambdas in C++, but just to give you a glimpse of what it involves, this is an definition of a class written in the form of struct. That's typically it is written because struct in C++ is also a class, but a class which has all its members as public, right? So there is no private member in a struct. Now, what we are overloading, we are overloading one operator. So there's an operator overloading. That operator is operator parenthesis, or which is called the function application operator. So basically, this operator can be used as a function application, and it takes a parameter int a. So this, just note this notation. There are two pairs of parentheses. The first pair of parentheses is basically the identity of the operator. Like you write operator plus, operator assignment. Similarly, you are writing operator function application. And then so when you apply this function, it takes a parameter a, and then it returns something, returns the same value here. I mean, we are not, so this is an identity operator basically. Now for this my class, we define an object, my object. And if we do that, then we can write int x is assigned my object 0. This is a syntax which you are not familiar with possibly, because after an object, you don't expect this function call operator to happen. But here, if you do that, it actually means that my object with function call operator 0 is referring to the overloaded operator function. So it is my object dot operator function application with the parameter 0. So it basically calls this function and returns a 0. So this is, in effect, finally x is initialized with 0. But this is what is known as a function object, because this is an object. My object is an object, but at the same time, it is capable of invoking a function. So this is called a function object or function actor. And from that, a common term for this is a functor, which will be heavily used in C++ in terms of defining the lambdas. Just a small example. This is just to be treated as an example. We'll come to the details of how to write what are the syntax constraints and so on at a later point when we get equipped for all of that. But just note from the beginning here, what we include is a special header from the and functional. So functional is something which includes things like the Y Combinator internally. And then we have defined a number of different lambda expressions. And so this is the way to write a lambda expression in C++. I think I mentioned it once earlier too. So this blank pair of square bracket stands in the place of lambda. It says you are defining a lambda. Then you have the parameter for it, which is int type, and then the function body. The return value is not shown in this because the type of the return value will be int type of the expression. So I is int, 3 is a int literal. Operation addition for int, therefore I plus 3 is it, so the return type will be int. So you may or may not, in this case I have not specified the return value. And then, therefore, what is 3? Right? So this is a function itself. So the type of that is difficult to write. So C++ allows you not to require to write this type. You can just say auto. Auto is a keyword in C++, which, so the compiler will deduce that it is a function from int to int and will place it accordingly. We go to the third line, which is actually I should have put the third line earlier. Which is easier, which is square, another function square, which takes int I and returns I star I, right? So that is auto. That is square, which has again an int to int type mapped. Then we say the twice application. So if I have to do a twice application, what I have to do, this lambda expression takes a function and a value and applies that function onto the value twice. Right. So if the given function is g, twice will, and the value is value parameter is v, then twice will apply g on the v twice. Right. It is g of v, and then you apply g on it again. That's twice. The question is, how do you pass this function g as a parameter? So for this, you have a template definition in functional known as function, which is written in this way. It basically, this syntax means that within the square bracket, what you write here first is the return type of the function. And what you write inside the parenthesis, and there could be, you can see the provides line here, there could be a number of different arguments. So it is a variadic definition. So it's a number of different arguments you can have here. So you can put those argument types separated by comma. Here we have just one argument. So this becomes a function type which takes an integer and returns you an integer. You can compare it with function pointer type defs in C, but this is a type-safe way of defining such a function type. And you take that function as a reference parameter, because certainly you do not want to copy that function. So that gives you twice. So once you have twice, you can define a composition also. So composition will take two functions g and h and a value v. so that it applies H on V first and then applies G onto that. The G and H are written in the same way using the function type from the functional. So once we have defined this, then we can, in the main, we can use them directly as we use the function. So these are all different lambda expressions. We have defined 3 variables with initialization here. I could have written int here. Just for illustration, I show it as auto to mean that, well, auto can be applied not only to function types, but for any type where it is deducible from the initialization of the value type. Right, so this will be inferred as int. Then if I call fa, that is this lambda will be evaluated. This lambda will apply on a, which is 7. So I will get a result which is 10. Similarly, if I have twice fa, then we will apply af on a twice as is defined. So I will get f adds 3. So 3 will be added twice on a, which is 7. So I'll get 13. Similar result I'll get with comp ffa also. If I compose, because twice fa is nothing but compose ff of a. Right? So a few examples. So this just gives us a glimpse that, well, it is not. I mean, while we are building the strong mathematical foundation of lambda calculus to equip ourselves for very strong formalisms in programming, they are also available in the common programming languages. So this brings us to the end of initial introduction to the lambda calculus syntax. Let me stop here and see if you have any questions. Otherwise, I'll continue to the next one. Any questions? So in this module, we have introduced the basic notion of lambda calculus, its definition, how to build the lambda expressions, and the concept of carrying multivariable function, higher order function, Y Combinator for recursion, and have shown that through a series of examples that whether it is a simple identity function or successor function, or it is Boolean algebra, or basic natural number system, or recursive functions, lambdas can model all of those uniformly using the same syntax. We have still not started talking about the semantics, the meaning of these, the types of these. So, for example, given a lambda expression, what does it actually mean? A complicated expression, what does it really mean? And we will come to talk about that subsequently. But this was just to make you familiar with how to write lambdas, and for simple lambda expressions, what do we understand by the lambda expression? What kind of functions do they represent? Right? Any questions? No, good. So
Sir,
in that case, yes.
so to obtain
yes,
a functional behavior, we could have just defined a function instead of writing an operator inside a structure. Like, what is the point of it?
Of the functor?
Yes, sir. Like in the previous case, we defined a structure and we defined a keyword called operator so that we can obtain a functional behavior.
Right.
Why do we have to do that? We could have just defined a function on that name, right? My object.
Absolutely. You are right on the dot. So let me just, I will not explain it in much detail, because I have a detailed explanation coming later on in module 6. Some of the ideas are, let's say, if you have a function, right, which you have to pass as a parameter to another function, right? We talked about higher order function. We talked about, say a function. You want to write a function which integrates another function, right? You understand? I want to write an integration function. Now that integration function could integrate x, it could integrate, let's say, I mean, obviously I'm not talking about indefinite integral, I'm talking about a definite integral. So I have a function, I have two bounds, a and b, and I want to integrate that function from a to b. I want to do that, say, for cos x from 0 to 1. I want to integrate x squared from, say, 0 to 25. I want to integrate, say, 1 by x from 1 to 3, and so on, right? Now, I want to write this integration function. There are several numerical algorithms to do that, right? For example, I can use trapezoidal rule, I can use Simpson's 1/3 rule, and so on. Now, the point is, how do I pass a function to this integrating function? So function becomes a variable, right? So if you do it in C, then you'll have to do it with a function pointer. The problem with the function pointer is it does not have a, I mean, all functions, say, from int to int has the same function pointer type, right? I cannot differentiate the type of x mapping to x plus 1 and x mapping to x square using function pointers. So if I can define, now what does have a type? In C++, a class has a type. Class is a type. So if I can define a class for my function, then I can use the objects of that class to mean the function as a variable. Functor plays that role. That I can actually, if I did not have this, then I have to pass this function to an integration function using just a function pointer. So I cannot do a type checking. I cannot do any reasoning on that. But if I use a class, if I can use an object which has a type in C++, then I can do all that. That is one reason that you use function objects. The second reason you will use it is a function or a function pointer does not have a state. A function pointer is just an address of where the function starts. So it can only invoke the function. But from one invocation to the next, it does not remember the state of the function. Right? So every invocation of the function is independent. So if I want to remember that whatever I computed in the first invocation, I want to remember some information from that and use it in the second invocation. For example, I'm just counting the incoming packets in the port. So if I want to do that, I have to use something like a local static variable and things like that, which are not visible, not accessible to anyone else because they're local to the function. Right? If I use a function object, I can use data members in the function object to remember the state. So being able to remember the state is something which is very, very important. And I can do that using a functor object. The third reason is if you think about a function, how do you invoke a function? A function, say sum, has two parameters a and b. If you say sum ab, or if you invoke this as sum a times b, comma c times d. You have two parameters, a times b and c times d. And then you are adding that. So it's a into b plus c into d, what you do in the invocation. Now, if you look at that invocation, then the evaluation of the parameter expressions like a into b and c into d are done, and then the function is invoked. And all this happen in one go. So you have to collect all the parameters expressions together when you call the function. Okay? You cannot, if you get this parameter expression from different points of time, you cannot keep them anywhere. You have to remember them in the program. Whereas if I have a functor object, then I can have parameters as data members of this functor object. And as and when I get a parameter, I can evaluate and put that parameter there. And when at a later point of time, when I think the parameters are all ready, I can invoke the function. So I can do a lazy evaluation of the function. That is, I do not need to collect the parameters, evaluate them, and call the function together. Collection of the parameters, their values, and the invocation of the function can be done separately. So there are several such reasons, and the dominant reason being that you can define a very proper type for the function. But I just gave a very qualitative reason here. I do not want to get into details because in module 6, when I discuss about lambdas in C++, I have at least 10 slides which explain what are functors and why you need functors. Okay, but this, since you asked, I just wanted to give you some insight into that. Is that okay?
Yes, sir.
Okay. Then let us move on to the next module. Is the slide visible?
Yes, sir.
Okay. So in the next module, we will little bit sidestep from lambda calculus, because I'm sure that bombarding you with a lot of theory will make it boring. So this module will give you an idea about functional programming, and we will talk about a number of languages which are based on this lambda calculus. So this is roughly what we will cover. So what is functional programming? You must have heard this term. So to appreciate what is functional programming, let's just review what is a function. And as we have seen, the function has strongly two connotations. One is mathematical. Right? Mathematically, we say this is a function. I started discussing module 2 with a formal definition of what is a function in mathematics. So it's a set of operations that perform some computation on the parameters passed and return a value. Right. So the basic property of a function certainly is that it takes 0 or more parameters, it returns a unique return value, and the fact that for the same set of parameters, the application of a function in mathematics will always return the same value. Right? A function in a programming language is something similar. Its purpose is to compute based on the parameters and return a value. But the deeper semantics differ in a significant way. For example, functions are often used to basically promote modularity. Why do we write functions in programming language? Because we want to break down the tasks into kind of small and roughly independent pieces. We can enhance, reuse, we can promote structured programming. It helps in debugging, maintenance, and so on. But the function as we see them in programming languages does not necessarily reflect a mathematical function. For example, functions may act more like a procedure. Procedure is also another unit of modularity. If you have ever looked into languages like Pascal, you would have seen actually procedure being available as a unit of computing module in the programming language. The idea behind the procedure is to accomplish one or more related activities, but not necessarily it would return a value. It may not return anything, or it may return multiple items. So procedure is kind of a generalization. So it does not basically represent the unique definition of functions in mathematics. So in languages like C, there are no procedures. So functions in C take on multiple roles. They could be mathematical type functions, like I define sin x. It's a mathematical type function. Or there could be functions that act as procedure. Right? I define a swap function. Right? It has no value to return. But it does create a side effect of swapping two values. I write a printf. It does return a value, but seldom we use printf for the value it returns, which is the number of characters printed. But we do it for the side effect that it puts the desired entities onto the output stream. So such functions, typically in programming languages, can produce side effect, whereas mathematical functions do not have side effects. So given this, a functional design, a function-based design has certain requirements. One is, there is a typo, functions are written twice, ignore that. Functions should be concise. What it means is every function should accomplish a single task or a goal. For example, think of the design of a stack. You would have seen in some textbooks or in some other material that the stack has to have a pop function which takes away the topmost element. You would have seen a signature of pop which actually returns that top element also. So it removes the element from the top of the stack as well as returns it. Now, this is not something that functional design would prefer. It is a one function for one task. So either it removes where it is pop, or it returns the top element where it is an operator, or where it is a member function top. Right? So conciseness of single function for single task is a basic requirement. Then it can return one item. That is, you do not allow it to return multiple items. So in C, we can achieve this by returning multiple values in a structure. If we have multiple values to return, then we can put them in a structure, much in the way we just discussed about handling of multiple valued functions in Lambda. So we can put them in a structure and return that. In C++, we can do this, obviously return by a structure, but also we can use reference parameters. So which basically is a side effect. So in C, if you return it by an encapsulation of a structure, or even in C++, if you do that, you still adhere to the returning one item requirement. But if you in C++ use reference parameters as output, so what you are doing is you are basically creating side effects. The third requirement, which is the strongest, is that it should have no side effect. Right? So many functions in programming languages, I'm just talking about the library functions only, have side effects. They are designed with side effects, like printf in C, or the sort function in C++, and so on and so forth. So the problem of functions with side effect in terms of functional design is that if you have a side effect, then the application of the function on the same parameter or parameters multiple times may produce multiple results, outcomes. If you have no side effect, then a function evaluated multiple times with the same parameter values will always give you the same result, right? So that uniqueness is what you want in the functional design. Naturally, that means that parameters have to be provided by parameter passing for communication, not use global variables, because global variables are necessarily side effects. And also functional design tends to exploit recursion whenever possible, because that simplifies the body of a function and requires fewer or no local variable. In fact, you can do without local variables altogether. So that's the approach of the functional design. So given this, functional programming is dealing with a program in a functional programming language is basically a function call, which in turn makes use of other functions, which is the basic building block, is a function. Functions will produce results. Now, up to this point, you will say that, well, C satisfies this. In C, basic building blocks are functions. A program is a function call to main. Functions produce result in C. But the second part is very important. They do not change any memory state. There's no side effect. Since there is no side effect, there is no memory state that you can change. You call a function, you get a value. You call another function, you get a value. In other words, pure functions will not have any side effects, right? So as I mentioned, the side effect is the main thing. So in functional programming, everything is an expression. There is no assignment, because assignment is a way to change memory state. In an imperative language like C, C++, Java, Python, a program is a sequence of assignments. And assignments produce the result by changing memory states. But in functional programming, that is not what we will allow. It is only functions and function calls, which are the building blocks of functional programming. Very, very different way of looking at it, which is kind of the way we build mathematics. To the next slide. So functional programming paradigm is one of the major programming paradigms. I think in the very first lecture, I talked about some of these paradigms. Imperative paradigm, or which otherwise we called procedural paradigm. They are referred, interchangeably by both these names, though these two terms mean little different things. Procedural paradigm means that it is algorithms first, that you primarily build the programs with the algorithms that you apply on the data. Imperative means that you basically do the computation based on a memory where you make changes to the memory. So it's a transitive changes on the memory which gives you the program results. They are used kind of interchangeably. So in that, C is procedural. Java is procedural also. It has procedures, but we say that it is object-oriented because that is the paradigm it strongly supports. In contrast, if you have seen the database, query language, SQL, the standard query language, it is declarative. Now, what is the difference between procedural and declarative? Procedural is where you say that do these steps and you will get the result. So steps are important, not the result. So I will say that successor is a function which takes a parameter, adds one to it, and gives me a value. I could have called this successor by the name immediate next. Does not matter. Because all that I'm interested is the fact that in terms of the algorithm, it takes a value, adds one, gives me back. If I were to do a declarative one, I will say that I have a declarative definition for successor such that for all x, successor x is x plus 1. Now, for a successor, this sounds trivial. So think about square root. Giving a declarative definition of square root is very easy. I will say that for all x, square root x gives me a number y such that y into y is equal to x. This is a declarative definition, but this does not tell me how to get y. So the procedural definition of that has to find an algorithm to do that. Like you could do, different, Taylor series expansion and stuff like that to actually find the procedure to find the square root. But the procedure will need all the steps to be encoded, whereas declarative just says that this is the property that I want. Right? So when you talk about SQL, standard query language, you do not specify as to how to get the answer to the query. But what you specify is what you want as an answer, the property. So it is based on, so declarative languages are often based on a mathematical foundation. And you write an expression in that calculus. So SQL is written on relational calculus or relational algebra. And you write an expression in that. So whatever satisfies that expression is your result. So functional programming is also the same. It is a type of declarative paradigm. We are saying that this is what I want as a result. Okay? It is also known as applicative programming or value-oriented programming and so on. The core idea is everything is a function. There's nothing other than a function. So you have primitives, kind of atoms like literal values, and you have functions. In lambda calculus, we have assumed that we have variables. Some functional programming even does not assume that. Everything is a function. It will be based on a sound theoretical framework. Like SQL as a declarative one is based on relational calculus. So SQL is not a functional programming language. It is primarily declarative, but it has several other things. But in a functional programming paradigm, it is certainly based on a sound theoretical framework, and majority of functional programming languages use lambda calculus as a framework. And several examples. Some of them are early functional programming languages, Lisp. I mentioned it at the very beginning itself. And then several hundreds of functional programming languages have evolved. In recent times, the most important languages are ML, or as is commonly used, SML. ML stands for meta language. SML stands for standard meta language. Based on that, Haskell, very popular these days. Miranda, Scheme is a kind of derivative of Lisp. It's called a dialect of Lisp, Logo, and so on. And at the same time, several common programming languages, which are procedural, object-oriented, multi-paradigm, are also imbibing the functional programming style as a part of them using the lambda calculus. So has C++, as Python, as Java, almost all, strong popular languages which are imperative also have functional programming dimensions. So the fundamental difference, therefore, is the design of the imperative languages is based directly on the von Neumann architecture, which is based on the fact that there is a store. There is a store to keep your intermediate values. There is a store to start with certain values and finally get the result, where efficiency is the primary concern, rather than suitability of that language for software development, in software engineering, or for that matter, say, the safety of the language, the robustness of the language, the provable correctness of the language. These are not concerns primarily of the imperative languages, but their primary concern is efficiency. Whereas the functional languages are based on mathematical functions, a solid theoretical basis, which we have started building up in module 2. And they are relatively unconcerned with the architecture of the machine on which the program will run. Obviously, finally, the machines are the same. Machines are built with the electronics, so they're the same. But you will make underlying layers to make sure that you don't have to be concerned with the von Neumann architectural nature of the machine. You can just build it on the mathematical foundation that you have. So that's the basic idea of the functional programming languages. I have to stop now because it's time. If there are quick questions, then I'll take, and we'll continue on the next class. Any questions?
Hello.
Yes.
Yes, sir. So I just wanted to ask that is the mutability of data structures like gone in functional programming? Because suppose
Yes.
okay.
Yes. Yes. Data is not mutable. Everything in that, you do not have a memory. If you look at pure function, then again there are shades. Then there are shades because some functional programming languages do sneak in with some imperative features as well. But in a pure functional programming languages, everything is immutable, like in Haskell.
So, but wouldn't that affect the complexity of some algorithms?
On the contrary, it actually makes things simpler. It's just a matter of our mental training to think about them.
Okay.
So that is the whole idea. That is the whole idea that I'm trying to. The reason I have introduced this in here are two. One is certainly I do not want to just bore you with theory and you lose connect. You'll ask as to why are we doing this. So we will show why we are doing this. And the second is to actually expose you to a number of different variety of functional programming languages on which you can write programs and see for yourself as to what are the trade-offs, what are the benefits that you get. How is it possible to write programs where you do not have mutable data? How is it possible to write everything in terms of a recursive form, and so on and so forth? Right? So that's the basic idea. So that's what we have started on with. We'll continue in the next class. And for some popular functional programming languages, we'll have somewhat details of syntax and an example use. And then with that, again, we will go back to lambda calculus and show that, okay, if functional programming languages are doing this, then what is the mathematical foundation? Syntax is not the only thing. You have to have semantics, you have to have types. So how do you actually mathematically define those so that these functional programming languages do follow that foundation? Right? That is the approach that we are trying to take. Right?
Okay, sir.
Okay. So let us, I mean, we are cross time. So let us stop here today. Have a nice day. And we'll meet on Wednesday early morning as well.